Hello, everyone. It is common that in your basic econometrics courses, they will ask you to derive the ordinary least squares estimator in the simplest case when you only have one explanatory variable, which is this one, right? So suppose that your dependent variable is y and your independent variable is x, and you are trying to estimate the parameters alpha and beta from this population equation. And most likely you remember from your courses that after you use this ordinary least squares method, what you will find is that your best estimate for alpha is alpha hat, which is basically just the difference between the average of your dependent variable minus beta hat times the average of your independent variable. And in this case, of course, beta hat is the estimate for beta, which is this ratio that I'm showing right here. Let me go back because I don't know what happened to my app. Okay. So that's what you're supposed to derive. And you may think that it requires many steps of a lot of algebra and calculus. Well, it's actually not a big deal, so fear not. Hope has arrived. Let me guide you through the process. It's actually pretty simple. So everything starts because we are trying to minimize the sum of the squares of the residuals. So our objective function is precisely this sum of the squares of this error term, which is defined as the observed value of your dependent variable minus the fitted values of your linear model. In other words, you're just trying to minimize the distance between each of the observed values of your dependent variable and the linear model that you are proposing. That's all. That's all that you're trying to do. So we're going to take first order conditions from this objective function. And the first order condition has to be the partial derivative of this sum of the squares of the residuals, which, by the way, I will summarize by saying this is just the sum of the squares of the residuals in this way. Because that's exactly what we have in parentheses, no? That's by definition epsilon hat. And first I will do it with respect to alpha hat. And according to the first order conditions, this must be equal to 0. So this first derivative is 2 times the sum from 1 to n of what we have inside the parentheses times the derivative of what we have inside the parentheses, which in this, with respect to alpha hat, no? Which in this case is -1. And this is equal to 0. I will call this one my equation number 1, just to have an order of in this process, okay? The second first order condition has to be same idea, because we are still optimizing our objective function, but this time with respect to beta hat. That is also equal to 0, right? Which means that this is also 2 times the sum from 1 to n of what we have inside the parentheses times what we have, the derivative of what we have inside the parentheses, but this time with respect to beta hat, which in this case is negative xi. And everything is equal to 0. And I will call this guy my equation number 2. Now, let's go in order. First, I will start working with my equation number 1. So if you divide both sides of the equality in equation 1 by -2, you will simplify this expression as the sum of what we have in parentheses equals to 0. And you know that the summation is also a linear operator, just as the expectation, which means that we can re-express this as the sum from 1 to n of all the yi's minus the sum from 1 to n of all the alpha hats minus beta times the sum from 1 to n of all the xi's equal to 0. And from here, it would be easier if you recognize that the first term could be re-expressed as n times y bar. Just by definition, right? The same with the last term is n times x bar. And the term in the middle, since we are summing n times the same constant alpha hat, this is exactly the same as n alpha hat. So I will re-express everything as we just identified in yellow. And this has to be equal to 0, right? So from here, it is just, hold on, I was missing something. I was missing the beta. I'm gonna say n times beta at x bar. Okay, now we're good. So from here, the easiest thing to do is to first divide both sides of the equality by n, and then I'm going to rearrange, okay? So just for didactic purposes, let me do everything step by step. And now what I'm going to do is to add alpha on both sides of a hat, on both sides of the equality. And by doing so, and I will rearrange, no? So by doing so, I will get rid of this alpha. And I'm gonna put the right-hand side as the left-hand side. And this will be alpha equals y bar minus beta hat times x bar, which is exactly the expression that we wanted to find, no? Of course, we're not done yet. This is just part of the answer. Now we would like to work with my second equation. Just to continue having a good order, let me call this equation number 3. And now I will say, well, from my equation number 2, and let me just scroll up to show you the equation number 2. What I will do is to divide both sides of the equality in equation number 2 by -2, similar as I did before, right? The expression has to be quite similar to what we have in the case of the first expression. So I will say this is the sum from 1 to n of what we had in parentheses before, which was y1, yi minus alpha hat minus beta hat xi times xi equals to 0. And from here, I will distribute the product. Which means that now I will have xi, yi minus alpha hat xi minus beta hat xi square equals 0. So the only thing that I did is to distribute the product. No? And from here, the next easy step is just to plug. I will actually call this equation number 4. And let me say plug my equation number 3 in my new equation number 4. So I will have my sum from 1 to n. And whenever I see alpha hat, which is right here, I will substitute for the actual value of alpha hat, which in this case is y bar minus beta at x bar. And going back to the expression that we have, this was multiplied by xi. And whatever we have left in the third element is exactly the same, not just xi squared. And everything is equal to 0. Now I will once again distribute the product between the elements that we have inside the parentheses that is in green times xi. This will give me my regular sum. The first element is the same. And now what we have is y bar xi plus beta hat x bar xi minus beta hat xi squared equals 0. So you see, it's just algebra, right? The only trick is to follow, it's not really a trick, no, but the suggestion is to follow an order. And you can do it in any order you want, but I think this is, to me, like the easiest way to proceed. And now we're gonna sum each of the terms, because remember that the summation is a linear operator. The first sum is between, is the sum of this product, no? Xi, yi, minus y bar is a constant, so I'm gonna put it before the sum. Plus beta and x bar are also constants. So I will also put them before the sum. So when I say constant, I basically mean that they don't have the subscript I, no? Because you know that beta hat is not really constant, no? Beta hat is a random variable. But what I meant is that they don't have the subscript, so they're not affected by the sum. And finally, here, since beta hat is also not affected by the sum, we're gonna put it outside the summation. Let's hope that we don't have any mistakes. I think everything is correct. And now let's simplify some stuff, no? Because there are interesting things to note here. For example, the fact that this sum could be re-expressed as n times x bar, just as we did before. Also, we're gonna do something similar for this one, is n x bar. And that's all that we can do. Going back, again, for deductive purposes, I will do step by step. This is now n times x bar, y bar, the second element, right? The third element is n x bar times x bar. So obviously that term is going to be x bar squared, no? And the last element we have is beta beta hat, and this didn't change, right? This beta hat, the sum from 1 to n of xi squared equals to 0. So from here, I would say probably the easiest thing to do is to factor out beta from the last two terms. Let me do that. So I would say, in this case, we have the first two elements completely unchanged. And my beta, which I think would be easier to, you know what? I'm gonna do the following. I will just re-express first as follows. I'm gonna add beta hat the summation of the xi squares and subtract n times beta x bar square. Okay, basically I'm subtracting the third and fourth elements from the previous equation. And with that, we are, this is just, again, deductive purposes. No, I don't wanna confuse anyone. You're supposed to, my understanding, you watch this video because you want some clarification on how to do this, no? So that's how it is re-expressed. And now, let me show you how this, when we factor it out, this should be the sum from 1 to n, the xi squared minus n x bar squared. And now, what I will do is to subtract what we have in the yellow expression in parentheses on both sides of the equality. And with that, what we will have is that beta hat is what we have in the numerator is exactly the left-hand side of the equation, of course. So it will be just the sum from 1 to n of the xi's yi minus n x bar y bar. And what we have in the denominator is the expression in parentheses in the yellow expression, right? So in this case, is the sum from 1 to n of all the xi squares minus n x bar squared. And the trick here is, because this is not exactly the same as the expression that I showed you before, no? But it should be easy to see that the numerator is equal to the product of the xi minus x bar and the yi minus y bar. And the denominator is in fact the sum of the xi's minus x bar square, but everything square. If you don't believe me, my suggestion is that you distribute the product here in the numerator, simplify, and you will find that this same expression that we have in the numerator from the previous equation. You should find it, but the trick is to start with this one, right? Same for the denominator. Start with the square in this summation. Distribute the sum, and you will find precisely the expression of the denominator in the previous equation. But it's easier to prove it in that way. Okay? So this is the expression that we wanted to find. So I hope this helpful video was actually helpful. No, I meant to say I hope this video was helpful to you. And if not, well, comment what improvements can we make, or if you want me to further explain something. But see you next time. Peace.